Why is it that fish can survive when the water above them freezes over? Well, it's partly because the densest the water gets is at 4 degrees Celsius. So, when you are when a when winter comes, all of the 4-degree water falls down to the bottom of the pond, and any other temperature of water moves to the surface. So if the fish can hibernate in 4-degree water, they can survive the winter, regardless of how cold it gets on the surface. So the density of water at the bottom, or the density of the water at the bottom of the pond, where it's 4 degrees Celsius, is going to be 1 gram per cubic centimeter. Now that density is not exactly a SI unit, so I'm going to convert grams to kilograms by saying 1,000 grams per kilogram. And then for the cubic centimeters, I'm going to say that centimeters goes on the top and meters on the bottom. And we will have 100 centimeters per meter, but I'm going to cube that. And what happens when I do this is it ends up being equal to 1,000 kilograms per meter cubed, which is reasonable because a cubic meter is pretty big compared to a gram. You're going 100 by 100 by 100, and that's a million cubic centimeters. So a million cubic centimeters divided by 1,000 grams per kilogram. Table 9.1 has some densities of common substances. What's the most here? Platinum with 21,400. It's 21.4 times the density of water at 4 degrees Celsius. And air is 0.00129 times the density of water at 4 degrees Celsius. By the way, all of these values are at standard atmospheric temperature and pressure, defined as 0 degrees Celsius and 1 atmosphere, which is 101,300 pascals. Now that is standard atmospheric pressure, and I'm going to use that number a lot. P of naught equals 101,300 pascals. It will come up a large number of times in this chapter. It is 101,300 newtons per meter squared. It is the maximum sucking pressure that you can generate, because if you generate a pure vacuum and put the outside to the air, the difference in those two pressures is 101,300 pascals. You cannot um, you cannot create a smaller than a vacuum. You can't create a pressure less than a vacuum. So this is getting ahead of myself, but I can actually calculate the maximum depth of a well that I could get with with the pump on top, which is from the density of water times gravity times our height. It's going to be 101,300. And with a pure vacuum on top, the maximum height of the well can be 10.33 meters. Now that was the density with water. What if I use the density of mercury? And mercury, I think, is Hg, oddly enough. I need the H in there. Let's calculate the height here. Here we get 0.760 meters, which is also 760 millimeters. And this is actually another unit that they use besides pascals to measure pressure. They would call this 760 millimeters of mercury. If you ever hear blood pressure readings, your high blood pressure between 90 and 120, and your low blood pressure being between 60 and 80, both of those are given in relative terms in millimeters of mercury from 760, or from whatever the atmospheric pressure is. So if, for instance, somebody said your blood pressure was 110 over 70, your high blood pressure would be 870 millimeters of mercury. That's the absolute. And your low blood pressure would be 6 plus 7 is 830. If you did it in absolute terms, that would be what your blood pressure was. So 110 over 70 would be relative to 760. 870 to 830 would be relative to the vacuum of space. So Quick Quiz 9.1 asks, suppose you have 1 cubic meter of gold, 2 cubic meters of silver, and 6 cubic meters of aluminum. Rank them by mass from smallest to largest. Looking at table 9.1, we have aluminum at 2.7 thousand kilograms per meter cubed. Gold at 19.3 thousand kilograms per meter cubed, and silver at 10.5 kilograms per meter cubed. 1,000 kilograms per meter cubed. Actually, that's kind of convenient because with that unit, you can either say 1,000 kilograms per meter cubed with an E3, or kilograms per meter cubed, or you can leave the E3 off and just say grams per centimeter cubed. However, they didn't do that with air, oxygen, hydrogen, or helium. You would need to put those in E3 to get those to work. This would be 0.00129 E3 times 10 to the third. So for this one, we'll multiply that by 1, we'll multiply this by 2, and we'll multiply this by 6. So once we multiply, we end up with the aluminum being the smallest mass at 16,200 kilograms, gold being the next, but very close to the silver with 21,000 kilograms. Example 9.1. Calculate the weight of a cylindrical column with height h equals 40 meters and radius r equals 1 meter. First of all, let's calculate this guy's volume. The volume is going to be the area times the height. The area is the area of a circle, pi r squared, times the height. So it's pi times 1 squared times 40 is 126 meters cubed. Part B, or no, we still haven't found the weight. Okay, so the weight is going to be equal to the mass times gravity, and the mass is the density times the volume times gravity. So we will have the density is 1,000 kilograms per meter cubed. That's the weight, mass, or the density of water, times the volume, 126 meters cubed, times gravity, 9.8. And that comes out to be, to 3 significant digits, 1.23 million newtons. Part B is calculate the force exerted by air on a disk of radius 1 meter at the water surface. So we want the force right here. And the key to that is that the pressure at the surface, or this is going to be generally this, we're going to always use this number 101,300 pascals or newtons per meter squared, and we're going to multiply that by the area. Force equals pressure times the area, and we saw that earlier as pressure equals force divided by area. But now we're going to use it this way. We'll use 101,300 for our pressure, and our area is pi times the radius squared is 1 squared. And that comes out to 318,000 newtons. So the force of the air is 318,000 newtons. The weight of the column of water is 1.23 million newtons. Part C is what pressure at a depth of 40 meters supports the water column. So this is going to use the pressure is going to be equal to the weight of the water column plus the force of the air divided by the area. We're going to use both of those together. So and let me actually show this. The weight, when we had it earlier, was rho times volume. Rho times volume is, and the volume was area times height times g. And the force of the air is pressure, the initial pressure times area. And we divide that by area. So you could cancel out area, area, area. And so it'll be rho GH plus P sub naught. So that's one way we could calculate it. Or we could use the things that we've already found. The weight, 1.23 E6 plus 318 E3 divided by pi. So calculating it as weight plus force of air divided by the area, I got 493,000 pascals, which is newtons per meter squared. Over here, using this formula, density is 1,000 kilograms per meter cubed times 9.8 for gravity, height of 40 meters, plus our 101,300 pascals. Also comes out to be 493,000 pascals. Question 9.1 says a giant oil storage facility contains oil to a depth of 40 meters. How does the pressure at the bottom of the tank compare to the pressure at a depth of 40 meters in water? Well, looking at table 9.1, it doesn't look like they give the density for oil, unless I missed something. So I Googled that, and it says the density of crude oil is 870 kilograms per meter cubed, which is considerably less than that of water. So plug in 1,000 for the density of water, plug in 870 for the density of oil, G and 40 and 101,300, and you can see 9.8 times 40. You can see that this will come out less, and 101,300. This will come out more. Exercise 9.1, a large rectangular tub is filled to a depth of 2.60 meters with olive oil, which has a density of 915 kilograms per meter cubed. If the tub has a length of 5 meters and a width of 3 meters, calculate A, the weight of the olive oil, A, the weight, which is mass times gravity, mass is density times volume, and the volume here, or the density is going to be 915. The volume is the width times height times length, so 3 times 5 times 2.6. Gravity is 9.8. So it comes out to 350,000 newtons. Now, part B asks for the force of air pressure on the surface of the oil, which is going to be force of air, which is going to be the pressure times the area. The pressure is 101,300, and the area is 3 times 5. Here, the air pressure turned out to be considerably more than the weight of the, or the weight of the air is considerably more than the weight of the oil. Finally, the pressure exerted upward by the bottom of the tub. So using the numbers we've already got, weight plus the force of the air is 350 E3 plus 1.52 E6, 1.52 E6 divided by 15 meters squared. And that comes out to 125,000 pascals. You can also do this with symbolically. The weight of the column is density times the volume, which is area times height, plus the force of the air, which is the pressure times the area. Divide that by the area. I forgot the G, density, mass times gravity. Cancel out area, and you get rho GH plus p sub naught.